So now we'll take a look at when we combine bending and axial loads on a column. So what we would call a beam column. This is a 10-foot length pin. So K equals 1, K effective equals 1. There's no other bracing other than at the ends in every direction. And there's a lateral wind load right in the middle. And then there is an axial load of 200 pounds of dead load and 2,000 pounds dead load and 3,000 pounds light load. So let's take a look. We talked a little bit about load combinations because once we get into the lateral loads, those we start getting away from just adding the loads directly. So let's start out with axial. So the way you handle a beam column, and we talked about this, we haven't done an example yet, but the way you handle a beam column is do the axial, just the way we've been doing, do the bending, just like we did for beams. And then you don't directly add them together, you use the interaction equation. So I'm going to go fairly quickly through the axial and bending because we've done several examples of both of those. Let's start out the demand side, so the load side. We would use load case number 2. So we talked about the load cases, and this is what we've been using all along, dead plus live. There's no factors on that. So this is not like the factors we use in LRFD. These have just the pieces of the factors related to not having full wind plus dead plus live. But dead plus live is feasible, and so that load case 2 is going to give us the biggest effect on axial. The stress is P over A. In this case, dead plus live would be 5,000 pounds over the area of the 6x8 column. And that's 121 psi. So that's our demand stress. And our capacity side is FC prime times FC, CD, CM, CT, CF, CP, CI are adjustment factors. Okay, so all of them are 1 except for CP, and we have to calculate CP, right? So to get CP, let's look at first of all, our L over D ratio. So we know K equals 1, K effective equals 1. It's a pin. We don't have bracing in either direction. And then our effective length over D depth is K equals 1 times 10 feet times 12 inches per foot over D of 5.5 inches. And that gives us 21.8 as an L over D, and remember we use that number, but we also have to check that it's less than 50, and that part's okay. All right, so let's do what we need to go into the equation to get C sub P. So we've got F sub CE, and that is that 0.822, and I look up my value for E, 580,000 psi. And 21.8 is my L over D ratio squared is 1,003 psi. Okay, so if any of this, if you're wondering where certain numbers came from, just go back to one of our direct axial examples. And we have the F star C, which is all of our values without including C sub P. And that'll give us, since they're all 1, that's going to give us just F sub C, which is 1150 psi. So that ratio, F sub C to F prime, or F star C, is 0.87. And then if I calculate C sub P, I get 0.64. So that's what I'm going to use in my final equation here. So FC prime is 1150 psi times a bunch of 1s times 0.64 CP, and I get 736 psi, right? So if I'm looking at just axial, so far so good. All right, so if I had zero bending and this was just an axial case, I'm way good, right? It's 121 to 736. So okay for axial only. Now we need to look. So if I'd gotten here and it's not even okay for just axial, then it doesn't meet. Okay. Now, if you ran into that on the test, you can rest assured that you probably made a mistake because I wouldn't have you stop at halfway through. So go ahead and calculate the bending just in case. But in real life, this is where I would stop and say this section, if this was, let's say, a 750 instead of 730, I know it's not going to meet combine axial and bending. So I'd stop and get a new section size or a new type. Okay, so let's look at bending only. Our demand side, now we're looking at wind. Okay, so let's look at load combination 5 for this one, and that is dead load plus 0.6 wind load. Okay, F sub B, so bending stress is my over I or M over S. Moment is PL over 4, right? That's the moment for a center pointed loaded beam. And that's basically what we have, just turned up on its side over S. So 0.6. So we don't have dead in that direction. So we've got 0.6 wind. Our wind was 500 pounds. L is 10 feet. And I erase these little drawings here. Don't run out of room. L is 10 feet. We need the 12 inches per foot conversion. And that top side is divided by 4. And then if I look up the S value, it's 51.56 inches cubed. And I get 175 psi demand on the bending stress. All right, so let's look on the capacity side. So good old F sub B prime, and then we've got the bending value we look up. And then we've got bending has the biggest slew of adjustment factors. So C sub D, C sub M, C sub T, C sub L, C sub F, C sub U, or FV, C sub I, C sub R. And all of those guys are, well, not all of them. So C sub D is 1.6. These two guys are 1. We need to figure out C sub L. And then these guys are all 1. All right, so go back and look that up yourself to make sure you're not missing any of them. And then C sub L, to find that, let's look at our D over B, and I get 7.5 over 5.5. Let me look at some real quick. Okay. Did I write the wrong depth? Oh, we were in the weak axis. So I just, here's a good thing I should point out. We were in the weak axis direction before, so that was D. Now I'm in the strong axis direction. So D is going to change, right? So weak axis D would be this way. Strong axis D is this way. I remembered we had 5.5 there, so I should point that out. All right, so D over B in the strong axis direction equals 1.31. So no lateral support required, and I get CL equals 1. All right. These 3 dots mean therefore, if you didn't already realize that. And F sub B prime is equal to 1500 psi, and bending times 1.6, and everything else is 1, so I get 2400. So we are way good on this one too. So little FB is less than FB prime, in other words, 175 psi, is much, much less than 2400. So we're okay in bending only. Oops, check bending only. Okay, so we're okay. Now is when we combine them. All right, so now combined. Right, so for this is in India, since this is the new section here, India 3.9.2. It's equation 3.9-3. And that equation, I'll write the full thing out this time, is little fc over big FC prime, that quantity squared, f sub b1. So strong axis is 1, and weak axis is 2, is f sub b. I'm just going to write this instead of copying this all out. You guys have this equation. So if you can't see what I'm writing, go there. And then there's the same equation, the f sub b2 one. All right, but this is 0 because this is bending, right? So there's no, we had weak axis stuff, but it was all axial. So f sub b2 is 0 because we didn't have weak axis bending. All of our bending is coming in the strong axis direction. If we'd had, say I have this column and I've got the load we had on there, and I also had one coming into the plane, that's when we would use the rest of that equation. It's just more numbers to keep track of. It's not necessarily harder, okay? And it's just keeping track of which direction you're coming from. And that quantity maxes out at 1, okay? And then f sub c over f sub ce2 plus f sub b1 over f sub be squared is also less than or equal to 1.0. I don't know why I put so many decimal places on that one. Okay, so we're going to look now at the load combination that has all the stuff. So we're going to use, so we got to go back and look at the combined load equation now. LC6, so load combination 6 is D, so dead, plus 0.75 live, plus 0.75 times the 0.6 wind, plus 0.75 times roof or snow or rain. All right. So what do we have? We've got dead, and we have live, and we for axial, and then for bending, we've got the wind load. Right, so note that this is different than so we can't just add this up. Okay, now we're combining the two. We did the other part to get some of these values in direct bending and axial, but we need to look at our new load combination here. Okay, so oops, all right, F sub C equals, switched colors on you there. Okay, I'm going to go to the next page. There we go. Okay, so the demand side, little f sub c, p over a is going to be the dead, right? This is the compression only part. We're axial only, 0.75 live over the area. Okay, so you can put those in and you'll get 103 psi. F sub b1 is bending strong axis, right? So that's only the wind part on the strong axis. And this is, again, PL over 4, that quantity over S, but I'm going to use the 0.6 times the 0.75, then times my wind load. I probably should have just left that be, but then times my wind load. I'll go ahead, 10 feet, 12 inches per foot, over 4 over S. It's the same as before, except for we're using this 0.6 times 0.75 times the wind load, and we get 131 psi. So why is it different? So this is because when we use the load equation with everything combined, we have a knockdown of to 75% of live, and then 75% of 0.6 wind. Okay, plus we don't have roof, snow, rain here. So when we put all three together, this is what we use as that equation. And these come from basically the probability that there's going to be all of these at the same time. We know dead load is there, and we know it pretty well. How much live we're going to have at the same time as the largest wind is much less chance. Okay, so that's where all those come from. So now we have the loads for that combination, and we know FB2 is 0, is weak axis. All right, so the third term then, right, the third term we had is 0, so let's look back at our equation. So we already marked that one out. FCE2, so let's look back at this equation. Sorry, jumping back and forth on you. All right, so this equation, we already marked out, that's 0. Now let's look at this equation over here. So any of the 2's are going to be 0. And this guy is going to be 0, and this guy is, sorry, this guy, and then this guy is for bending, biaxial bending, weak biaxial bending, okay, is this guy. So we're going to end up with this equation is not going to come into play either. Okay, so this equation number, if you want to look at it, is 3.9-4. So go take a look at that section just as a reminder. And it tells you what each of the terms are. Okay, so now we're ready to put this all together. So we need to check bending alone. We check axial alone just to make sure that those guys are fine. And then now we're going to look at, because they have to go under a higher load case. All right, so now F sub C prime, this is going to be 1150 times a lot of ones, and then you can recalculate your C sub P in here, and you get, and I'm going to let you do that, 1306 psi. F bending strong axis is going to be 1500 times 1.6. Yeah, that's the same parameters, 2400 psi. Okay, so we go and calculate the same type of values, FCE for the strong axis, and we get 1862. So just follow the process. You don't actually have to go back and calculate each of these. I'm just showing you kind of what the process looks like. We're just filling in the parameters into the equation 3.9-3. All right, so now let's go back to the main equation. 103 psi over 1306 psi squared plus 131 psi over 2400 psi times the quantity 1 minus 1 over 3 over 1862, and we get 0.06. Okay, so this just has to be less than or equal to 1, right? Because this is the interaction curve that I showed you. And so, yes, this is fine, but it is Okay, way over designed is what I would say this is. Right, so we had way over designed pure axial, way over designed bending. But even when we put the two together, it's well over designed. Okay, so we could use a much smaller member. Or I shouldn't say much because it doesn't take much to start causing problems. Smaller member, but we were just asking this case to check to see if this is right, and it looks like it is okay. All right. So you could take this another step if you want to, obviously if this was a problem and I said design it, then you'd start out with something. And I might have probably gone to a smaller member just for the heck of it as soon as my axial load was so far over, or maybe check bending and axial by themselves. If you've got a spreadsheet that does this, it's very easy to check sizes. So, this is way over designed, pretty small loads for this column size. So what were we using? We were using a 6x8. You might try least down to a 6x6, which also gives you, although you don't even need that because you really only need you only need the strong axis in the direction of the bending. So it would be this direction, right? So, you could try a 4x6, something like that. It's hard to say what would actually work, but you take it down from here. Okay, so you see what I'm saying? You've only got lateral loads in one direction, so there's not really a need to use a square post or column, but you could definitely do that too. So you could try a 6x6. All right, or in this one, maybe even a 4x4. All right. Anyway, if you've got a spreadsheet, that makes it a lot easier to go through these samples. So that's the end of the example here. Basically, you do the axial, you do your bending. After you've checked them separately, you come in, you need to do the combined load case, which reduces the load when you put the two of them together. Then you have to do the interaction equation. If all that works, then you're good.